this lecture, we shall define when a mapping is surjective, and we shall prove a lemma that states that the composition of two surjections is again a surjection. Consider a mapping f from A to B. Now for the elements of the codomain B of f, we may distinguish three possibilities. First, it may happen that there is exactly one element in the domain of f that maps to it. Second, we may have the situation that there are two or more elements in the domain of f that map to it. And finally, we may also have the situation that there are no incoming arrows, that there is no element in the domain of f that maps to this particular element of the codomain. A mapping is a surjection if for every element in the codomain there is at least one element in the domain that maps to it. So by saying that a mapping is a surjection, we exclude the latter possibility, that there are no incoming arrows. A surjection is sometimes called also surjective, so we use the adjective surjective to say that a mapping is a surjection, or sometimes we say that a mapping is onto. Let's consider a couple of examples. First, let's consider the mapping f from integers to integers, defined by f of x is x squared minus 1 for all integers x. Then this mapping is not a surjection. This can be easily seen by considering the Cartesian graph associated with the mapping. Note that, e.g., the number 2 has no incoming arrow, since there does not exist an integer x such that x squared minus 1 equals 2. If we restrict the type of f by considering it to be a mapping from the set consisting of the integers minus 1, 0 and 1 to the set consisting of the integers minus 1 and 0, then f is a surjection. Indeed, for both elements in the codomain, we can find elements in the domain that map to them. For 0 maps to minus 1, and both minus 1 and 1 map to 0. Next, consider the mapping from real numbers to real numbers with the same specification. It is not a surjection for many reasons. One reason is that minus 2 plus 1 is not the square of a real number. But we may restrict the codomain of f to be the interval from minus 1 to infinity. Recall that the interval notation is just another way of specifying the set of all real numbers greater or equal minus 1. This mapping is a surjection since for every real number y greater or equal minus 1, there exists a real number x such that x squared minus 1 equals y. Let's now express the property of being surjective as a formula of predicate logic. Mapping f from A to B is surjective if and only if for all y in B there exists an x in A such that f of x equals y. The property will be considered as the definition of being surjective or onto. If some mapping is surjective, then we know that it satisfies the property of surjection, and conversely, if some mapping satisfies the property of surjection, then it is indeed a surjection. We shall illustrate the two-way use of the property of surjection in the proof of a lemma. Let A, B and C be sets, and consider two mappings, f from A to B and g from B to C, then because the codomain of f coincides with the domain of g, we may compose these mappings. And we can state the following property. If f and g are both surjections, then g after f is a surjection too. The lemma is a conditional statement. We put the condition that f and g are both surjections in a flag, and set as our goal to prove that g after f is a surjection. Proving that some mapping is a surjection amounts to proving that it satisfies the property of surjection. Note that the property of surjection is formulated for an arbitrary mapping f from A to B, where f, A and B should be interpreted as meta-variables. Let's find out what the property of surjection entails for the mapping g after f. Note that here g after f is actually a mapping from A to C. So we instantiate the property of surjection, taking g after f as the mapping, A as the domain, and C as the codomain. Hence, to prove that g after f is a surjection, we need to establish that for all elements z in the codomain C of g after f, there exists an element x in the domain of g after f, such that when g after f is applied to x, we get z. With the universal quantification introduction, we further simplify the goal. Let's picture the situation. There are sets A, B and C and mappings F from A to B and G from B to C, and there is an element Z in C. And we need to establish the existence of some x in A such that G after F maps x to Z. We proceed in forward reasoning mode. We start with an application of the property of surjection on the assumption that G is a surjection. Note that we should instantiate the property for the mapping G with domain B and codomain C. We then get that for all Z in the codomain C of G, there exists a Y in the domain B of G such that G of Y is equal to Z. We can eliminate the universal quantification with the already declared Z in C and subsequently apply existential quantification elimination, declaring a witness Y in B such that G of Y equals Z. Another application of the property of surjection, this time for F, yields that for all Y in B, there exists an x in A such that f of x equals y. We have a y in B with which we can eliminate the universal quantification and then get, also with an application of existential quantification elimination, an x in A such that f of x equals y. It remains to combine all the available facts. Starting with G after F applied to X, by the definition of composite mapping, this equals G applied to the result of applying F to X. Then, since f of x equals y, in G applied to f of x, we may replace f of x by y. And then we may use that G of y equals z. We have found an x in A that is mapped to z by G after f. Thereby, our derivation is now complete. We proceed to transform our derivation into a more readable proof. Let's first state again the lemma. It consists of a declaration of A, B and C, F and G, and states as a main goal to prove that if F and G are both surjections, then so is their composition. Backward reasoning is used to simplify the goal. First, to prove the if-then statement, the if part is formulated as an assumption, and the then part becomes the new goal. The new goal is to prove that G after F is a surjection, so the property of surjection can be used for further simplification. Since application of the property of surjection yields a universal quantification over elements in the codomain of G after F, we declare an arbitrary element in the codomain and state as the new goal to prove that there exists an element in the domain that maps to it. The proof continues in forward reasoning mode, applying the property of surjection. First for G, and then for F. The proof is completed with a straightforward use of the definition of composite mapping and other valid facts. Here you see the lemma and its proof. We end this lecture showing again the pictorial representation of surjective mappings. A mapping is surjective if for every element in its codomain there is at least one element in its domain that maps to it. This concludes our discussion of surjective mappings. In the next lecture we shall discuss injective mappings.